Hello Chem 2A students. I am here at Pasadena City College in the very lab room SV20 that we would have been doing our labs in if remote instruction hadn't taken us all online. I'd like to show you a demonstration of how a Bunsen burner works. Even though we won't have the opportunity to use one ourselves hands-on, it's very helpful to see an up-close and personal demonstration of the Bunsen burner, know the parts of the Bunsen burner, and when our future labs that we discuss refer to heating something with a Bunsen burner, you have a better idea of how that process would take place. So if you would take a look at experiment 1, page 1-5, where it talks about part 4, a look at a Bunsen burner. Notice the first thing you're asked to do in part A is sketch the Bunsen burner. Notice you're asked to label parts of the Bunsen burner, and let's take a look at those right now using this Bunsen burner as an example. So just a quick sketch of it, does not have to be sophisticated at all. I'm given to stick figures myself when I draw. But you see here that there's a base to the Bunsen burner. I'm pointing that out right now. There's a gas flow. In other words, there's an intake that connects to a tube which is linked to our gas source, and that gas flows in through the tube into the metal inlet that the tube slides onto. There's an air entrance valve, and that valve is located right here. Right, if you get close, you can see that there's holes and air can move in, and I'm kind of wrestling with it. That air entrance intake, there we go. I shut it off so you can see that now there's basically no opening. Be very difficult for air to get in, and air is needed for the burning process to happen. So now I can rotate that air entrance valve and create an opening, and you can see that this one is kind of stubborn. Remember us when you find your way in life and maybe make a donation for better Bunsen burners. So there's an air intake valve that should be more easily adjustable than this one is, right? There's the barrel or the mixing tube, and that's where the gas that's coming from the natural gas source mixes with the air coming into the air entrance valve and mixes together to supply the combustible mixture. The flame is going to, of course, be on the top of this. Let me go ahead and just light a Bunsen burner and show you what that flame looks like. So because this valve is kind of sticking, I'm going to switch over to this other Bunsen burner. Now, a comment about lighting a Bunsen burner. You first of all want to make sure that that gas inlet, so this valve here, adjusts the flow of the gas coming in from the gas inlet. So we have a gas valve adjuster here, gas inlet here. Want to make sure that the gas valve is turned on, right? You want to light the match first. Don't start the gas running. Don't know if you can hear that sound. The gas is coming out, but there's no flame source to light it, and that's a hazard because the room is now filling with this flammable gas. So you always want to light the match first with the gas valve off. Now I'm going to come over, turn the gas valve on, and bring the match up from the side so that I don't blow the match out by holding it right on top of the flame when I light it, and it can just blow right out. Notice that I deposited that match in this little metal can that looks like it ought to be a Christmas present, but in fact it's just a wrapping for a metal can where we can safely dispose of our match, not flick it into a trash can where it could ignite a paper towel. Right, so here we see the flame to the Bunsen burner. And let me point out, you are asked to draw in your diagram, there is a larger, darker blue flame that I am outlining, and then there is a lighter blue cone-shaped inner flame. So you're told to draw the flame showing the outer cone, darker blue, and then the lighter cone, which is triangular shaped on the inside. Okay. Notice that part B wants you to explore what happens when you don't have enough air to completely burn or sufficiently burn the natural gas that's coming out of the valve source. So it's asked, what is the appearance of the flame when the air intake is covered? And hopefully, very good, this air intake more easily adjusts. So I closed it. Now air can't enter in through the holes, and what's the first thing you notice? You lose that lighter blue triangular inner cone. So I can cause it to come back by opening up that air intake. You see it reappears. That means that this flame is getting sufficient air. Or I can close it off. The sound changes as well, and you lose that inner blue cone. If I really sealed it well, right? So notice what happens here, and this is what this question is really trying to fix on. So now I'm sealing it off so that really no air is getting into the barrel or the mixing tube. And notice that the flame becomes tinged with a yellow color on the top. That's a signal that there is a lack of oxygen, insufficient oxygen to completely burn the natural gas. You can see this appearance of a flame if you look in a fireplace. And if you've looked in fireplaces, you'll see all this black, sooty deposit on the fireplace. That's coming from this yellow tinged substance. That's actually carbon atoms that are forming because there's not enough oxygen to completely burn the carbon atoms in natural gas and form carbon dioxide. So that yellow color there is what we call soot, S-O-O-T, soot, like in a chimney. And you can collect that soot. Maybe let's switch hands here. I'm going to do a better job of sealing it with my right hand. You can collect that soot. So here is an evaporating dish. It's resistant to high temperatures. It's porcelain, white on the bottom. But if I hold that evaporating dish in this yellow portion of the flame and hold it there sufficiently long enough for a sufficient period of time, that white porcelain is going to become black tinged in color because of the soot, the carbon atoms that are attaching to the bottom of it. So I don't know, it's not been held long enough, but my eye can already see that I've discolored the surface of this evaporating dish compared to the white on the inside. It's now beginning to turn a darker color. And if I take a paper towel and scrape it along, right, it's hot now, I don't want to do that right this moment, but if I scrape it on the white paper towel, I'm going to see a black streak left. This carbon substance, carbon atoms, also known as soot. So if you look at the questions, what is the appearance of the flame when the air intake is covered, right? We've just noticed here you lose the inner blue cone and the flame becomes yellow in appearance. What is the deposit on the bottom of the evaporating dish? It is soot, right? So that soot is coming from this yellow color, which is carbon atoms, right? So what is the deposit on the bottom of the evaporating dish? Carbon atoms or soot. And where did the deposit come from? It was the result of insufficient air, specifically oxygen in air, to completely burn the natural gas, which contains carbon in the form of methane. Part C is wanting us to now look at a properly adjusted flame. So I'm opening back up that air intake valve. There you see that inner blue flame appearing again, and it wants us to investigate where's the hottest part of the flame. So we are instructed to take a piece of nichrome wire and try positioning that nichrome wire in different spots along the flame. And how long does it take for the nichrome to start glowing red? So first column, resting on the top of the metal barrel, how long does it take for the nichrome wire to glow red, indicating that it's hot? And the answer is, it's not glowing red. And we could hold it here a very long time and we're not going to see it glowing red. So this portion of the flame is a relatively cool part of the flame. Okay? Now we're going to, right? Now we're going to, and you're hearing me adjust, or you heard the blowers coming on in the classroom, and the airflow is affecting the flame. So I'm hoping we don't lose it and it doesn't go out. Let me try adjusting again here. Okay, just above, just inside the inner blue cone. Right, so we saw that go off. That's again because we had the air conditioning kick on in this room and it's blowing our flame out. Same things happens to students when they're doing a lab. So let me try closing a little bit here, and we will okay, inside the inner blue cone. All right, so we're going to hold that nichrome wire right here, 1, 2, 3, 4, 5, 6. And I would say between 5 and 6 seconds it takes for that nichrome wire to start glowing red inside the blue cone, inner blue cone, just above the inner blue cone. So I'm going to start with a new cool piece of nichrome wire, fair comparison, and we're going to try right here, 1, 2, and you can see it takes like all of 2 seconds for it to start glowing red right at the tip of the inner blue cone. Faster, shorter period of time than in the middle of the inner blue cone. And then lastly, at the tip of the whole flame itself. So right here, 1, 2, 3, 4, 5. So maybe 4 to 5 seconds. Again, this is relative, but longer period of time than the tip of the inner blue cone. So what we've realized from this demonstration is if you want to obtain the greatest amount of heat transfer in the shortest period of time, hottest part of the flame is right here, tip of the inner blue cone, right there. So it's asking here on page 1-5, right, for you to make a sketch of the burner flame. Notice just the flame. You don't have to redraw the Bunsen burner itself, just the outer blue cone, inner blue cone. Label the hottest part of the flame, which is right at that tip of the inner blue cone, along with the outer cone and the inner cone. And then lastly, last section here, part D, so turning over the page, we now want to get an approximate temperature for the hottest part of the flame, tip of the inner blue cone. So here's what we're asked to do. We're asked to take a piece of copper, right? Now this copper wire has been used multiple times, so holding here, it's kind of got an oxide on it, but right here you can see that characteristic reddish gold color of copper metal, which is confirming that I'm using copper here, not nichrome. For nichrome is a grayish metal all the way throughout, steely color. So I've got copper here as evidenced by that reddish gold color right there. This other black material is an oxide that's on the outer end. So you can scrape that off and reveal that red gold color of copper metal. Right, so we're going to ask the question, is the tip of the inner blue cone, is it at a temperature high enough to melt copper metal? So let's see what we find here. And it takes a really steady hand. Notice you saw a green color there. that is the color of copper when it is excited, in an excited state because it's been energized. So this flame is tipped with a green color. And there we go. I just saw that end kind of shorten. There it is, it shortened again, right? Because the copper metal is converting from the solid state to the liquid state, phase change, right? And melting right there on the tip. You should be able to clearly see it becoming blob-like as the copper converts from the solid state to the liquid state. A phase change. And again, that green color, if you've enjoyed the experience of fireworks as I have, you're basically seeing a little mini fireworks show here. Elements will release characteristic colors when you energize them through heat or electricity. So there's molten liquid copper metal right there on the end of the wire. It just moved again. And if I take it out of the wire, it's still glowing red, but you can see it cooling down. You see that liquid state, now that it's cooler, is solidifying, turning back into the solid state. So what we can conclude is we're not exactly sure what the temperature is of the hottest part of the flame, but we know this: it must at least be as hot as the melting point of copper, which is 1083 degrees Celsius. And I'll write that on the board in the class after this video is finished. It has to at least be a temperature of 1083 degrees Celsius to melt the copper. What about nichrome? Will it be hot enough to melt nichrome? So here is nichrome metal, holding it in the hottest part of the flame. You see it glowing red. Now, glowing red does not mean it's melted. It just means it's hot, it's energized, right? But it is not a liquid. It actually has to convert into that kind of a fluid-like state, which we saw at the end of the copper wire as the copper liquid kind of formed a bulb, right? So I do not see that at all. It's glowing, but in fact, I see no evidence at all that any sort of liquefaction is taking place. And I know I should hold this as long as I held the copper. I haven't quite given it the amount of time, but I have done this many, many, many times in my teaching career here at PCC, and that nichrome wire is not going to melt. We can hold it here all day long. That nichrome wire will not melt. What is the melting point of nichrome? Well, nichrome is an alloy. It's a mixture of metals, so it's a little trickier to answer that. You'd have to know the specific type of nichrome mixture, but it's approximately 1360 degrees Celsius. So this temperature is roughly 300 degrees Celsius higher than the melting point of copper, 1360 degrees Celsius, and that tip of the inner blue cone is not hot enough to melt the nichrome. Thank you so much for working with me in this demonstration of how a Bunsen burner works. And one last thing, right? I'm suddenly remembering, I wanted to give you an explanation as we look through procedures later on this semester of how you'd actually use a Bunsen burner to heat. So this is a ring stand. It holds a metal ring. And notice when I put the ring on the ring stand, I'm kind of eyeballing where that inner blue cone will be and adjusting the ring so that it's somewhere in the region of the tip of that inner blue cone above it. This is a wire gauze, and we commonly heat substances in evaporating dishes. You're going to see that looked at, that procedure described in experiment 3, our salt sand mixture. Once you have your ring stand, or your ring stand, your ring, your wire gauze, your evaporating dish set up, you place your Bunsen burner underneath it. Make sure the gas valve is adjusted to allow the proper flow of gas into the barrel. The air intake is adjusted. Light the match, bring it up from the side, and you are in a position here to heat something using your Bunsen burner. You can control the amount of heat by either reducing the amount of gas that's coming in, or often I have found myself in labs holding the Bunsen burner by this rubber portion here, which is not hot, and just moving the flame back and forth underneath the evaporating dish or underneath a beaker to control the heating. And so this is how we would be heating a sample of something in an evaporating dish. Of course, another option is to heat a substance in a beaker. So we can put a beaker on and do the heating with the beaker. So these are examples of how we would carry out a heating process in the lab. Thank you so much for being with me here in SV20 at PCC.